Howdy, folks. All right, we're going to move on to a new subject here, and this is it's a really good subject. It'll really help you understand the world, and it's a very useful subject. So what I'm going to explain to you this very first video is I'm just going to explain to you the basic formulas for what it is we're going to understand. What we're going to start learning about is we're going to learn about how populations that grow or shrink over time, how we can calculate how many there will be in the population. So let me give you an example. You know, we got the population of Earth, for example, and over time the population of Earth grows. And there are good reasons to try and understand, for example, how many people will be on Earth, let's say in 30 years. And there are formulas that we can use to calculate how many people will be on Earth in 30 years. Or let's say if you've ever seen a movie like where lots of people are dying from a disease, right? And we want to understand how many people are dying or how fast that they're dying. And we want to know how long it'll take before everybody's dead, okay? That's a population shrinking over time. And there are formulas that we can use to understand that. Now, there are other kinds of populations that grow and shrink. If you think broadly, instead of just using the word population to mean people, we can also understand populations of deer. We can understand populations of insects like mosquitoes. And then we can even understand populations of plants and the cells of plants. We can even understand things that aren't even living. For example, if you have a bank account, your money that's in the bank account, that is a population of money. It's a certain amount of money, and in order to grow, you need some money in the bank, and that's your savings. Your savings that's in the bank, that's your population of money. Similarly, you might have investments in the stock market or something like that, and the value of your investments, that's a population. That's a population of your net worth, of your monetary wealth. And that can hopefully grow over time, but sometimes it might shrink over time. So here's what we're going to do. We're going to try and understand the formulas. There's some very basic formulas that we can understand, but each of these formulas has certain variables in it. And you have to understand all the variables in order to understand these formulas, okay? But the first thing you have to understand before we do this is you have to understand that in order for a population to grow, you have to already have some of the population. The formulas that we're going to look at are based on an existing population. And so for example, if on the Earth there are no, as far as we know, there are no dinosaurs. And therefore, the reason that we can answer the question, how many dinosaurs will there be in 30 years? There will be no dinosaurs. Well, how do you know there will be no dinosaurs in 30 years? Because there aren't any dinosaurs now, presumably. I mean, I don't know for sure, but I don't think there are any dinosaurs. So one thing you have to understand about populations that grow or shrink over time is, well, especially growth, in order for a population to grow, there has to be an existing population. And so what it is that we're talking about, this whole subject, is the subject of exponential growth. So everything that we're going to learn about right now is we're going to learn about exponential growth. In particular, we're learning about eventually we'll learn about exponential functions. Now, exponential growth or exponential decay. Decay is when the value shrinks. Exponential functions are a special kind of function. They are functions whose value is based on their previous value. Every other function that we have looked at, every other trigonometric functions, if you've seen, well, you may not have seen those yet, but you've seen polynomial functions, quadratic functions, linear functions. None of those functions require that there be a previous value in order for there to be a next value. But exponential functions are a very special kind of function that indicate that the growth of the function is based on the previous values of the function. For example, let's say that we have one zombie. Somehow you use these stories about zombie apocalypse, right? There's one zombie, and the idea is that every time a zombie bites a human, that human then turns into a zombie, right? So one zombie bites a human, that human turns into a zombie, and now there are two zombies. Each one of those zombies, there's two zombies now, each bites a human, and now there are four zombies because each one of these zombies made another zombie. Now there's four zombies. Now each one of those zombies bites a human and makes a zombie, and now there are 8 zombies, then 16 zombies, then 32 zombies. This 2, the population 2, is based on the fact that there used to be one zombie. This 4 is based on the fact that there were 2 zombies. This 8 is based on the fact that there were 4 zombies. And so what you can see here is every number, so let's say this is at the very beginning at time 0, that's a t, it's supposed to be a t, 0. Then after 1 day, there's 2 zombies. After 2 days, there's 4 zombies. After 3 days, there's 8 zombies. After 4 days, there's 16. And after 5 days, there's 32 zombies. And the idea here is that the number of zombies that we have today is based on how many zombies we had yesterday. That is what we call exponential growth. Exponential growth is growth that is based off of how much the population was before. So your bank account, if you have $0 in the bank today, then you will have $0 in the bank tomorrow because you don't have any money to grow. Now, you may say, well, what if I go to the bank tomorrow, Mr. Ryan, and I put $100 in the bank? Well, that's not exponential. That's you putting money in the bank. That's a different situation. That came from your paycheck, which was probably linear growth. So you took linear growth from your paycheck, and then you went to the bank and deposited $100. Now that there's money in the bank, even if you don't put any more money in the bank, that money will sit there and it'll grow slowly over time because the bank will use that money to lend out to people, and then the bank will pay you interest. Okay, so if you don't have any money in the bank, if you have 0 in the bank, then you'll have 0 tomorrow. But once you put money in the bank, that money can start growing exponentially. Same thing with zombies. Right now there are no zombies, but if we somehow or another manage to get one zombie, that one zombie would become 2 zombies. Those 2 zombies would become 4, then 8, 16, 32, and eventually the whole world would be taken over by zombies. Okay, this is an example. This is what we're talking about. This is exponential growth, or exponential decay if it's shrinking. Okay? So in order for you to understand populations that grow or shrink over time, in order to understand the formulas for exponential growth or exponential decay, there's a few variables I need you to understand. There's basically 5 letters that I need you to be aware of. The first one is P. Now, it doesn't have to be P. I've seen other letters used here. Traditionally, I have always used P, and in the fields that I have worked in, P is the value that's used. P basically means principal or population. It's the starting value. It is the starting value. The starting value before the exponential growth takes place, or at the beginning of our measurement of the exponential growth. We can say starting value or the starting population. That's P. That's a part of the form. That's one of the letters in the formula. Then we have the letter R. You're going to want, listen, if you're not writing these down, you need to write them down right now. You got to know these letters because you're going to be asking me, what does this letter mean? And I'm going to say, go back to the video. Okay, so R. What is R? R is the percentage. It's a percentage. It's the percentage rate of growth or of decay. Growth is growing, decay is shrinking. So when something decays, it breaks down and gets smaller. Okay? It's the percentage rate of growth or decay turned into a decimal. Turned into a decimal. Now, here we go. You have to be good at turning percentages into decimals, because in this formula, I'll tell you the percentage rate of growth, but then you have to turn that percentage into a decimal and put it in the formula. So, as a reminder, let's say that you have 43%. That's 43 decimal percent. The decimal point is over here, right? And what you have to do is you have to move that decimal point over 2 places, or you have to divide by 100. So if we do 43 divided by 100, that is equal to 0.43. So 43% is equal to 0.43. We're taking the 43%, we're taking the decimal point, we're moving it over 2 places, so now it's here in front of the 4, and that's 0.43. So 43% is the same thing as 0.43 as a decimal. And you're like, yeah, I'm fine with that. I don't have a problem with that. The problem comes when it's 5%. You say, Mr. Ryan, I know what 5% is. 5% is equal to 0.5. No. Listen, you only move the decimal point 1 place. I told you you have to move the decimal point 2 places. And what you're going to say is, but Mr. Ryan, there aren't 2 places to move the decimal point. And I'm going to say, I understand you don't see 2 places to move the decimal point, but there are 2 places there. There is a 0 in front of the 5. And so you're going to move that decimal point over 2 places, and it's going to be 0.05. So 5% is equal to 0.05. Okay, you have to move that decimal point over 2 places, and you got to fill in zeros. Remember filling in zeros in synthetic division? Well, sometimes you have placeholder zeros. There's a placeholder 0 here. This is really 0.05%. That's what 5% is. It's 0.05%, which means 0.05% is equal to 0.05. Another way you can do it is if you have 5%, divide 5 by 100. And if you divide 5 by 100, that's equal to 0.05. Another way to think about it is 5 divided by 100. If you go to the denominator and move this decimal point over 2 places so that it's 1, and you get rid of these, you have to move this decimal point over 2 places, so it's 0.05 divided by 1, which is 0.05. But in my opinion, if you have a calculator, the easiest way to do it is just divide your number by 100, and that'll tell you the correct decimal, especially when you see something like this. Let's say you have 2.46%. So I've seen so many people turn this into just 2.46. We didn't move the decimal point at all. No, you got to move the decimal point. You got to move it 1, 2 places. What's in front of this 2? There's a filler 0 there, isn't there? There's a placeholder 0. So it's 0.0246. 0.0246. And yes, it's okay to have that many numbers there. Okay? And if you take 2.46%, right? 2.46%. If you take 2.46 and divide it by 100, it's going to give you 0.0246. So make sure you turn your percentage into a decimal correctly. Okay? So R in these formulas, when you see an R, in place of the R, you are going to put a decimal number that was converted from a percentage. All right? Well, since I brought up decimal number, you might say this. What if your percentage rate is 200%, right? 200%. Well, where's the decimal point? It's right here. And if we move it over 2 places, it's going to go 1, 2, and where's it going to be? It's going to be 2.00. Well, what is 2.00? That's just 2. So is it true that 200% is 2? Yes, that's exactly what 200% is. In fact, we can take our 200%, we can take 200, divide it by 100, and what's 200 divided by 100? Sure enough, it's 2. Yes, 200% is equal to 2. 500% is equal to 5. 700% is equal to 7. And 750%, well, 750%, well, that's equal to 7.5. because we're moving the decimal point over 2 places. And if we put it right there, we have 7.5. Okay? So you have to know how to turn a decimal or a percentage into a decimal. You're also going to have to turn a decimal back into a percentage when we solve for r. So when I give you a question and I say, here's all the information, what is the percentage growth rate? You're going to have to solve for the r, and then whatever the percentage is, you're going to have to move the decimal point over 2 places and put a percentage sign on it. Okay? So r is a percentage, and then you have to turn it into, well, r is the decimal, and then it is turned into a percentage. All right, let's see here. Now we're going to move on to t. T stands for time. T in the formula, the letter t is a time variable. It's the time period of r, this r. Okay, so typically when you're given this r, for example, you'll be told that the percentage rate is 7.3% per year. 7.3% per year. That means that time, t, is in years. Okay, whatever is after the word per, this is the t units. So here, for example, if the question then says after 19 years, if we're dealing in years, you would put a 19 in for t, and that would be your t value. Okay. Now, every once in a while, you'll see something like 13.4% per hour. Per hour. So if your rate of growth is given in hours, then your time variable is number of hours. Okay, so this can change. This isn't always years. It can be days if the rate is given in percentage per day. It can be months if your percentage rate is given in per month. Okay, so time is, the time variable is the time period of the R percentage period, okay? If it's the per period, okay? That's T. All right, let's move on to the next letter. Our next letter is N. N. There we go. N. Now, N is the number of times the population grows. The number of times the population grows in a single T period. Oops. In a single T period. So, let's say that your R is a percentage per year. That means T is measured in years. And then what if the problem says that the population is growing monthly? Well, monthly, how many months are there in 1 year? 12. So in that case, N would be 12. Okay? So, if the question says that it's growing, that the population is growing monthly, or is compounding, really that's the word you're going to see, is compounding. It might say growing monthly, okay? So monthly means 12 times per year. How about weekly? Well, weekly, that would be 52 times per year. How about semi? Write these down, because all of these problems are going to be word problems. And in the word problem, it's going to say monthly and weekly and semi-annually. And I am not going to tell you on the test how many times a year semi-annually happens. Semi-annually means N is 2. That means twice per year. See what else I have. How about annually? What if it says annually? Well, annually means once per year. That means N equals 1. What if it says daily? Oops, daily. Well, daily, how many times does that happen in a year? 365, because there's 365 days in a year. How about quarterly? Quarterly. How many times does that happen in a year? Quarterly means 4 times a year. Okay? So, N, if time is in years, then monthly is 12 times a year, weekly is 52 times a year, semi-annually is 2 times a year, annually is once a year, daily is 365 days in a year, or times in a year, and quarterly means 4 times a year. What if we had hourly? But now, what if time? What if T is in days? What if our percentage rate is per day? And then we say that it compounds hourly. Compounds hourly. Well, how many hours are in one day? 24. So N would be 24. So you have to use correct units here. You're basically doing a conversion of units. If T is in days, and then, or what if this percentage rate, what if this is a per hour? What if it's growing at 3.7% per hour, and then it's compounding every minute? Well, how many minutes are there in an hour? Well, then N would be 60, because there's 60 minutes in an hour. So that's what this N means. It's the number of times that the population grows in a single time period. Now, you are only going to see this N variable when you are dealing in what's called discrete growth. And I haven't explained that yet, but I will in a few minutes. So this N, you're only going to see it when we're dealing with discrete growth. And I'll explain that in a few minutes. Now, the last letter is the letter E. So let's talk about E. E is not going to show up in all of the formulas. In fact, typically what you're going to see is whenever you see N, you won't see E. And whenever you see E, you won't see N. That's because N only shows up in discrete growth formulas. E only shows up in continuous growth formulas. And E is actually not a variable. E is actually a constant. So you are never, ever going to plug a value in for E. In fact, I'm going to show you something in just a second. Hang on. Okay, I have a calculator here, right? A scientific calculator. In fact, you are going to need a scientific calculator for this part of the class. So you have to have one of these. You could use your phone, except you can't use your phone on the test, okay? Here's what I want to show you. If you look really close on here, you're looking for a button that says ln or log. Here it is, ln. Let's see. Can you see that button? I'm getting too close. See ln right here, ln. And look at the green right over top of ln. Do you see what's there? It says e, I don't know if you can see that, okay, e to the x power, okay? That's what e is. In fact, it might have e on here somewhere else. Nope, I guess not. So watch what I'm going to do. I'm going to type in, I'm going to hit second, and then I'm going to hit ln, and it gives me e to the power of, and I'm going to put e to the first power, because e to the first power is equal to e, okay? All right, so now I'm going to press enter, and you're going to see what happens. Did I hit enter? Oh, I hit the off button. That's not the right button. All right, I'm going to hit enter over here and watch what it does. There we go. See that? 2.718281828. All right, that's what E is equal to. It is. This E. Now, there's a lot more to it than that. All you have to know for now is that it's approximately equal to 2.72 or 2.71828. E is the exponential base of continuous growth. And if you don't care about that, that's okay. But I want you to know that whenever you see E in a formula, all that means is that you're going to go into your calculator and you're going to key in E. That's it. Okay, it's a part of the formula. Okay, so if you see 72e to the power of 0.19 times 4, then you would just go into the calculator and you would key in 72, then you'd hit second ln, which would give you e to the power of, then you'd put in 0.19 times 4, and you'd press enter, and you would get 153.9558. Okay? That's how you use E. You're just keying it in. So E, you're going to put a number in for P, a number in for R, a number in for T, and a number in for N, but you are not going to put a number in for E. E is already a number. It's kind of like pi. You know how pi is approximately equal to 3.14? Well, E is approximately equal to 2.72. Okay? So that's what we're going to do. All right, so now that you understand all the letters, now that you've seen all the letters, let me show you the 4 formulas. There are only 4 formulas, and I am not going to give you the formulas on the test. You are going to remember the formulas. Or you're not going to remember the formulas, and you're going to fail the test, and then you're going to fail the class, and then you're not going to graduate from high school or from this class or whatever it is that you're studying for, okay? So you have a choice. You can either memorize the formulas, or you can not pass math. Those are your choices, okay? All right, so here we go. We have 2 situations, 2 kinds of growth. We have discrete growth and decay, and then continuous growth and decay. Let me explain the difference between the 2. Discrete growth, these are values or populations that do not grow all the time. They only grow like one time per month, or in the year, in a whole year, they only grow 12 times. Or in a whole year, they only grow 4 times. This is your bank account. So you have $5,000 in the bank, and then on the 7th day of the month, the bank gives you your interest on your money, okay? And the amount of money in your account goes up. One time. Then it stays the same until the 7th of the next month, and they give you some money, and it goes up. Then it stays the same for 30 more days, then it goes up, okay? That's called discrete growth, because the word discrete means clear cut and separated, okay? So the growth, the times when this value, this population grows are clear cut and separated. Continuous, on the other hand, these are things that are constantly growing. We can't point to when they grew. The human race, for example. The human race has been growing ever since people were first on this planet, okay? And we've been growing ever since. Right now, as we speak, we are growing. Since this video started, we've probably had 7 babies born throughout the world. Maybe 700 babies throughout the world have been born, because the human race is continually growing. Therefore, the population of the human race is growing continuously, okay? And there are other babies that are going to be born, let's say 8 or 9 months from now, right? They're brand new in their mother's bellies, right? And their cells, the number of cells, are growing continuously. They're constantly growing. Those cells that are building up that baby into a little human being are just populating and multiplying and growing and growing and growing and becoming bigger and bigger. That's happening continuously. Those cells, they don't wait until like midnight and then bam, grow, and then sit around and wait for 24 hours until midnight the next day and then bam, grow again. Those cells are growing continuously, okay? So we have 2 different formulas for discrete growth versus continuous growth. Also, we have, remember I said that here we have populations that grow or shrink? So, when a population grows, it's called a growth formula. Okay, so we can have discrete growth, and we can also have continuous growth. We also have what are called decay formulas. Okay, we can have discrete decay and continuous decay. Decay is when the population is shrinking. So this is 4 formulas altogether. There's the discrete growth formula, the discrete decay formula, the continuous growth formula, and the continuous decay formula. Let me show them to you. I'm just going to give you the formulas, you write them down, and then in the next video I'll show you how to use them. Okay? The discrete growth formula goes like this. A population, the value of a population, how many are in a population, okay, is going to be equal to P, the starting value, times 1, the number 1, plus R over N, close parenthesis, to the power of, remember I said it's an exponential relationship, so we're going to have to the power of, we're going to have an exponent, to the power of N times T. This is the discrete growth formula. And so you would put in a value for P, a value for R, a decimal value. N, remember N is how many times in one time period does it grow. Here's N again, whatever number you put down here, you got to put that number up here. And then here, T for time, that's how many time periods it's growing. So like if it's growing over 17 years, we would put a 17 here. If it grows 12, monthly, that's 12 times a year, we'd put a 12 here, a 12 here. And if it's growing at 5%, we would put 0.05 here. And if we started with 1 million, we'd put 1 million here. Okay? So there's the discrete growth formula. The discrete decay formula is the same formula, only instead of having a plus here, it's a minus. That's because decay has a negative R. R is negative instead, but we put the minus right here. So the decay formula is P times 1 minus R over N to the power of N times T. So there's the discrete decay formula. Now let's go over to the continuous growth formula. Remember this one, the continuous formula, instead of having an N, because it doesn't grow only a certain number of times in a time period. This is growing continuously all the time. So you can't say it only grows 12 times per year. This is growing 5 trillion times a year because it's continuously growing. Here's the formula for continuous growth. P again times E to the power of R, that's the percentage rate as a decimal, right? To the power of R times T, times time. And that's, sometimes we call it the PERT formula because it's P-E-R-T. P times E to the power of R times T. All right? Now, last one, the continuous decay formula. It's the same formula, P times E to the power of, instead of R, it's negative R to the power of negative R times T. There we go. And there's our continuous decay formula. Those are our formulas. You have to memorize these formulas. You are about to use these formulas over and over and over and over and over again. And anytime you have a problem, almost every time you have a word problem, your task is going to be, well, which of these 4 formulas should I use? And there's a very easy way to understand. Typically, you'll know it's a continuous growth formula because you'll see the word continuously in the sentence. Growing continuously, decaying continuously. Okay? All right, that's all I have for you in this video. In the next video, we'll work out some problems with exponential growth and decay. Okay?